Welcome to 5.6. We are looking at logarithmic and exponential equations. Our objectives for today are to solve logarithmic equations, solve exponential equations, and then solve them both using a graphing utility. So using your graphing calculator, Desmos, the app, the website, whatever it is that you graph on and feel most comfortable, we'll be able to solve these things algebraically and with a graph. So let's take a look. The first thing I wanted to cover was just a reminder that our logarithmic form can be rewritten into exponential form. Remember that both forms use the same base and the logarithm is equal to the exponent. So here we can see our base of 3 is our base of 3. Our log itself equals what we have in our exponent. So if you weren't able to figure out any sort of way to remember before, this little diagram actually, I saw it and I really liked it. And I like how they are putting emphasis on the log being equal to the exponent. It kind of makes it a little bit easier to remember how to rewrite. So our first example is solving these equations, and what we want to focus on is solving them algebraically and graphically. So first let's go through algebraically. What would we do to solve this? We have log base 3 of x minus 5 plus log base 3 of x plus 3 equals 2. Well, the first thing that I want to talk about is the domain. So I want to put emphasis on making sure we're staying in our domain when we find our answer. So the domain in our logarithms has to be greater than 0. So that's where we'll start. Let's find the domain. So we're going to take each piece inside of our logarithms to find their domain and make sure that they stay greater than 0. What this means is we're looking at x minus 5 has to be greater than 0, and x plus 3 has to be greater than 0. So if x minus 5 has to be greater than 0, that means that x has to be greater than 5. If x plus 3 has to be greater than 0, that means that x has to be greater than negative 3. So what this tells me is that x needs to be greater than negative 3. And that will satisfy them both. So whatever we find in our answer, we just need to make sure that our x is greater than negative 3. That way we stay in our domain. All right. Now that we have that out of the way, let's use some of our log properties and condense these two logs down into one log. So we have a log plus another log, and that tells me to use my product property. So I have a log plus another log. That tells me that I can turn these two logs into one log, base 3, and I have a product inside of my log of x minus 5 and x plus 3. And it's still equal to 2. We didn't do anything with that guy. Now I can rewrite this using my exponential form, which makes it a little bit easier for me to solve. And this tells me that my base is 3, my exponent is 2, and it equals x minus 5 times x plus 3. Now that I have it rewritten, I can FOIL these. So I have 9 equals x squared plus 3x minus 5x minus 15. I'm going to move this 9 over to the other side. This is now all the way back to algebra class where we are solving for an x and we're probably going to factor. So let me move this 9 over. And we get something that looks like this. We've got an x squared minus 2x minus 24 equals 0. I can factor. We have x, 6 and 4 make 24, and the sum can make 2 if I have a negative 6 and a positive 4. Now we solve, we get x equals 6 and x equals negative 4. Please review factoring if this is not coming back to you. It will greatly benefit you if you just take a moment, go review some factoring, maybe do a few practice problems. That way these are not difficult for you. Now, why did we look up the domain? And this is the exact reason why. We have two x values, and looky there. This one is not in our domain. And since that's not in the domain, then we can solve and say x equals 6. Now let's take a look at what this is going to look like graphically. I've preloaded these in here, and what we're going to do is graph the two that we have. Now you might be looking at what my graphs look like. The functions I've put in here, I have used the change of base formula. So if you look at my red line, the function I've used, I've done the change of base already. So I did the log of x minus 5 over the log of 3. And I'm adding that to the log of x plus 3 over the log of 3. And that's just our change of base formula. Separately, the blue line is x equals 2. I'm graphing each side of the equal sign. And then we can see right here that our value is 6 where they intersect. That's our solution. So we can check it. There it is. They intersect at 6, and that's what we calculated algebraically. So we're doing good. Let's do another one. All right, we've got log of 3x minus 3 minus log of 4 equals log of x plus 1. Again, I want to start with my domain, just so that way no matter what I find as my answer, I can make sure that it's even worth looking at. So this tells me, I'm looking at my logs, it has to be greater than 0. So that means 3x minus 3 is greater than 0, and x plus 1 is greater than 0. If 3x minus 3 is greater than 0, that tells me that 3x is greater than 3, and x is greater than 1. And if x plus 1 is greater than 0, that tells me that x is greater than negative 1. So my domain is x greater than negative 1. And that will satisfy them both. So let's take a look here. We've got a few logs, and just like our last problem, we kind of want to condense these down into one log before we can solve for that x. So I see a minus in between these two logs, and that tells me use your quotient rule. So that's what we'll do. We will use the property and condense these two logs, the first two logs here, into one log. We have log, and it's a base 10, so there's no base there showing, and that just tells us it's our common log. And our numerator is 3x minus 3, and our denominator is 4. So this is inside of our log. And the other side we didn't do anything with, not yet. Now, I can use my equality property because I have log of something equals log of something. The bases are the same for both of these logs, so that tells me what's inside of these logs must be equal. That means 3x minus 3 over 4 must equal x plus 1. Okay, and now we just use some algebra to solve for our x. Let's get rid of that 4. Whatever we do to one side, we have to do the other. So we have 3x minus 3 equals 4x plus 4. Now let's use inverse operations to move some things around. Minus 3x minus 3x. We have a negative 3 over here, x plus 4 over here. And then let's subtract our 4, and we will get x equals negative 7. All right, let's double check that it's in the domain. Our domain is x has to be greater than negative 1, and negative 7 is not. So this is not in our domain. And since it's not in the domain, then we don't have a solution. This symbol is like the empty set, no solution. It is telling us there is no x where these values will be equal. Let's find our graphical view. Here we go. We'll zoom out. We'll see what these guys are doing. We have log of 3x minus 3 minus log of 4 in the purple, or in the green, I'm sorry, and then log of x plus 1 is in the purple. And we're just trying to find when they will intersect because that tells us the solution. And you see what's happening there? They're both moving up infinitesimally small. And they just keep going and going and going and going. And I'm not going to keep moving that way, but they're never ever going to reach. They're both increasing, and so out of our domain. Okay, let's try another one. Here we have the log of x plus 4 equals the log of 5x plus 1 plus the log of 2. Again, the first thing I want to do is check my domain. That way I know what are my boundaries. We have x plus 4 must be greater than 0, and 5x plus 1 must be greater than 0. Now, if x plus 4 is greater than 0, that tells me x is greater than negative 4. If 5x plus 1 is greater than 0, 5x is greater than 1, so x is greater than negative 1/5. And so here we have x is greater than negative 4. All right, now we can solve algebraically first. Again, I see a log plus another log, which tells me use your product property. So log of x plus 4 equals the log, and inside of this log we have another product. We've got 5x plus 1 and 2. Again, these properties only hold true when all the logs are of the same base. Okay, now we have a log of something equals log of something. So let's set those somethings equal to each other, right? When a log of something equals a log of something, that means the insides of the logs equal each other. X plus 4 equals 5x plus 1 times 2. Now we can work our algebra magic and solve for x. X plus 4 equals 10x plus 2. And let's subtract some things. Minus x, 4 equals 9x plus 2, minus 2, 9x equals 2, x equals 2/9. 2/9 is greater than -4, so we have solved. And we can check this algebraically. Here we can see in black is log of x plus 4, and in orange red is log of 5x plus 1 plus log of 2. I suppose it could be copper. And there they intersect. At 2/9. Okay, moving on to our second objective, solve exponential equations. And I keep putting our logarithmic to exponential form because we're using that a lot. So, okay, we're going to solve these algebraically and also look at them graphically. Here we have 3 to the x plus 1 equals 7. Well, we want that x, and it's difficult to get it when it's up there. So what we're going to do is rewrite. Using the rewriting helpful hint up there, we can rewrite 3 to the x plus 1 equals 7 as the log base 3 of 7 equals x plus 1. And we're just rewriting it from exponential into logarithmic form. I'm probably thinking, why would I want to go back to logarithmic form? Well, for one reason, this part right here is just a number. We don't have a variable in it anymore. So we can throw that in a calculator and get a number out. And what that means is good news for us, because on this other side, we just have x plus 1. So let's get x by itself. So we have log base 3 of 7 minus 1 is what x equals. So we can put this in our calculator because log base 3 of 7 is something we can use the change of base formula with. Log 7 over log 3 minus 1. And if you throw that through your calculator, it should be giving you approximately 0.77124, maybe? Okay, let's do another one. E to the 2x minus 3e to the x minus 4 equals 0. Okay, now this one, we are going to work with our bases of e, and I'm going to be using some exponent properties on these. So the first one I'm going to look at is this e to the 2x power. And what I'm going to do is I'm going to rewrite him using that power rule, pow pow multiply nil, e to the 2x I can rewrite as e to the x squared, because remember, if I have a power raised to a power, I multiply them, and x times 2 is 2x. So I haven't changed the value of it, I've just rewritten it. Everything else stays the same. 3e to the x minus 4 equals 0. Now, this is a really funky looking polynomial, really. We have e to the x squared, 3e to the x minus 4. So we have something squared plus something not squared plus a constant. And in this case, they're negatives. So what we do with these things, usually when we're solving for an x, is we factor them. So this is going to be factored. And how do we get e to the x squared? Well, that's just e to the x times e to the x. How do we multiply to get negative 4 and add to get negative 3? Well, that would be a negative 4 and a positive 1. So we can factor that just like any other number. As I, in my brain, substituted e to the x as the x variable itself, the whole thing, just so that way I could factor it. But yeah, we've factored it out, and now, since I have one thing times another thing equals 0, just like when I'm factoring any other numbers this way, I set each one equal to 0. E to the x minus 4 equals 0, and e to the x plus 1 equals 0. So e to the x minus 4 equals 0. Well, that's e to the x equals 4. And the inverse of e, just a little side note, the inverse of e is natural log. So if I want to take the inverse of e, so that way I can get that x alone, then I would take the natural log of both sides. Natural log of this and the natural log of this. So natural log cancels out e, x equals the natural log of 4. If we throw that through the calculator, the natural log of 4 is about 1.386. Now if we solve the other guy, e to the x plus 1, that leaves me with e to the x equals negative 1. I do the same thing. If I take the natural log of both sides, then I'm left with x equals the natural log of negative 1. I want you to pause it right now and put that in your calculator. What's the natural log of negative 1? It can't do it. It's not going to give us one. So that's not an answer. Here we've got our x. Happy day. Okay. Our last example, 2 to the x plus 2 power equals 6 to the 2x minus 5. Now this one is a little bit tricky because if we look closely at it, we've got exponents with variables on both sides of our equal sign, but that's not the tricky part. The tricky part is the bases are not the same. So when I'm working with these things, before, in the problem before, we had all bases of e. In the problem before that, we were looking at just one exponent variable solving. This one, we've got two that have variables, but the bases are not the same. So what we're going to do is we are going to just take the natural log of both sides. That's where we're going to start. So I'm going to take the natural log. You know what? I'm probably going to just write it not in a script. Natural log of 2 raised to the x plus 2 and natural log of 6 raised to the 2x minus 5. Because whatever we do to one side, we have to do to the other. So we're going to take the natural log of each of these things. Now, if I use the power rule, now that it's in a logarithm, I can use the power rule and bring those exponents down in front. So I've got x plus 2, natural log of 2, equals 2x minus 5, natural log of 6. Okay, so now we have these products going on. What we have to do is distribute here before we can get our variable alone. We're kind of breaking that parentheses apart by distributing. So we have x natural log of 2 plus 2 natural log of 2 equals 2x natural log of 6 minus 5 natural log of 6. Now we can use our inverse operations to move things around. That way we can get everything with an x on one side and everything with no x's on the other side. So let's move this. We'll subtract x natural log of 2. So we'll be left with 2 natural log of 2 equals 2x natural log of 6 minus x natural log of 2 minus 5 natural log of 6. And then we can move the 5 natural log of 6 out of there because it doesn't have an x. Plus 5 natural log of 6. So this leaves us with 5 natural log 6 plus 2 natural log 2 equals 2x natural log 6 minus x natural log 2. All right. Now, all the numbers on this side are just that. They're numbers. We don't have any variables in that side. It's all calculatable. We can throw it in a calculator and get a number out. On the other side, that's where our variables are. And we're still trying to get our x alone. Notice that we have an x in each of these terms. And when we have an x in each term, that means we can factor an x out. So that's what I'm going to do. Oops. Five natural log of 6 plus 2 natural log of 2. And then if I factor an x out of both of these things, I'm left with 2 natural log of 6 minus natural log of 2. Now, this portion that we factored the x out of doesn't have any x's in it. It's a number. It's something we can throw through the calculator and get a value out. Since it has no more x's in it, I can divide it off because there's a multiplication happening between the x and what's in parentheses. So I'm going to divide by that 2 natural log of 6 minus natural log of 2. And whatever I do to one side, I have to do to the other. 2 natural log of 6 minus natural log of 2. So these cancel, and x, I'm left with 5 natural log of 6 plus 2 natural log of 2 over 2 natural log of 6 minus natural log of 2. And that we can throw in our calculator. Each of these numbers is inside of our natural log. In case you were getting confused, I apologize. But if we throw that through a calculator, it should approximately be 3.5792. I would encourage you to work through these, and at bare minimum, if you're not writing them down yourself, throw the finishing answer in a calculator and make sure that your answer matches up with mine. A big mistake that I see happen quite often is students will write out their work. All the work is flawless. The setup is perfect. The answer, when they write it, it's there. It's written correctly. And then when they put it through their calculator, they mistype and get the wrong final answer. So please double check your answer with mine. Make sure that you are in fact plugging it into your calculator correctly. That way, if there are issues, you can bring them up ahead of time and you'll know right away how you're doing. Some of the things that I would like to go over before we end are what these exponentials look like on the graph. So here we have 3x3. Oh, that's not the right one. 3 to the x plus 1 in the power. Okay, there we go. And y equals 7. So we're looking at when 3 to the x plus 1 equals 7, and we can see right there our answer. We had thrown that into our calculator and we had gotten approximately 0.77124, and we can see that's showing up right there. At 7 we get 0.7712. For the next one, e to the 2x minus 3e to the x minus 4, and y equals 0. When we had solved that one, we had gotten approximately 1.386, and if we look here, 1.3863. So there we go when those solve graphically. And for our final one, when we had those two functions with the two different bases, and we have to zoom way out, we can find that they intersect way up here, and we were finding that it algebraically we found 3.5792, and here we go, 3.579. So I just wanted to show you those graphic problems. If you need assistance with your graphing, please let your instructor know right away. Otherwise, I do expect that you are doing your guided notes for this section and completing your discussions and assignments in my lab.